In this video, I'm going to talk to you about the electrostatic force and the electrostatic field. You guys already know that when you rub a piece of fur against a piece of plastic, electrons will transfer from the fur to the plastic. This leaves my plastic charged charged negatively. It gained electrons charged negatively. The fur lost electrons and is now charged positively. Well, I'm going to talk about the electric force right now, because around this rod there's extra electrons on here. That's a negative charge, and it can exert forces on other charged objects. Paper is a polarized object. Notice I'm able to pick up this paper with just the charged rod. I can pick up paper and it sticks to the bottom there using a rod I've charged. Now, why does this seem extraordinary to us? Because we're so used to gravity pulling things down. Now, that's okay, gravity pulls things down, but while I'm lifting up that paper, is gravity still pulling down on it? Yeah. So let's talk about what's stronger, the electrostatic force or the gravitational force. With the gravitational force, you have the entire Earth pulling on things down with its mass. Gravity pulls with mass. So the mass of the entire Earth is pulling it down. The electrostatic force pulls with charge. I just have a few extra electrons on here pulling this up. And with a few extra electrons, I'm able to beat the mass of the entire Earth. You see, my friends, the electrostatic force is so much stronger than the electrostatic force. Oh my. I think I've misspoke. The electrostatic force is so much stronger than the gravitational force that a few dinky charges can pick up a piece of paper even when the entire Earth's trying to pull them down. So if you want to talk about which force is stronger, the electrostatic force is much stronger than the force of gravity. You can see that in the constant. Both have similar formulas, where the gravitational constant G is equal to 6.67 times 10 to the negative 11th, where the electrical force constant, Coulomb's constant, is equal to 9 times 10 to the positive 9th. That's a huge difference. Okay, on the order of times 10 to the 20th, the electrostatic force is way bigger than the gravitational force. Both of those forces are field forces. And what do I mean by field forces? I mean, you don't have to make contact. You don't have to push it like a force normal or something. A field force acts over a distance that there's nothing touching it. And both the gravitational forces and the electrostatic forces follow the inverse square law. So they're both divided by r squared. You see that with field forces, this sort of similar shape where they're inverse square and they reach out through empty space. Anytime you want to make an electric force, you have to make a charge. You charge up an object, you bring another charged object, maybe a piece of paper that happens to be charged, and there's a force between them. It's the same force on both of them, because there's only one formula for force. Newton's third law says it has the same force on both of them. But what if this force wasn't here? Would there still be something around here from the charge on here? Yes, we call that the electric field. Just like if you hold a mass above the Earth, Earth's gravity pulls it down. But what if there's nothing there to fall? Is there still gravity at this location? Well, we call it a gravitational field. If nothing is there to fall, it doesn't mean Earth's gravity ceases to exist at that point. It's just in the form of a field. So these forces move out in fields.
Teachers, please excuse the interruption for afternoon announcement.
Okay, so if anytime around a charged object you have this electrical field, you may be wondering, is there a way to detect it? And there is. This device is called an electroscope, and it's designed just for detecting electric fields. It has a metal top that's insulated from the metal shell around it, but then there's a leaf inside. It kind of looks like a post, and that leaf will turn when an electric field comes towards the top. Let me show you. I'm going to charge this up and bring it towards the top. Now I bet you'll notice, I can't quite see it from here, yes, that post is turning as I bring this near. That post is turning when I bring this near. Now, that means it's detecting an electric field. One neat thing you can learn about electric fields is you can shield them and block the electric field. And all you have to do is put a conductor around it, and in that conductor, I'll put a conductor over that. That conductor is going to catch that electric field, and it's going to prevent the electric field from getting to that detector. So you notice now the leaf is not moving. Okay? We have other examples I want to show you, a few other things. That's the electroscope that detects electric fields. This device is known as a Van de Graaff. The Van de Graaff has a belt underneath it, and it's designed to generate huge electric fields up here to the point it can even spark and shoot off electricity from it whenever you get near it. So there's a large, like that, ow. A large voltage that builds up and a lot of sparking. Now, one of the things people often do if they ground themselves, and I wasn't grounded, but if I separate myself from ground where the charges won't leak off me, and I put my hand on here, I will build up the charge as well. And this is commonly done, and then on people's heads, their hair tends to stand up. And so you might see people with a Van de Graaff generator touching it, and you see pictures of the hair standing up. I'm going to do a couple other demonstrations with it. Oh, why would their hair stand up, by the way? Well, the hair would stand up because like charges repel each other. And so if you have two of the same charges on your hair, you charge up just like this, you're all full of negative charges, that's going to cause your hair to stand up because your hair is full of a bunch of charges that repel each other. Now in here I have some crispy rice. It's kind of like Rice Krispies for poor people. And I'm just going to turn this on just for a moment. Notice what happens? The crispy rice flies out. Now why is that? Because, love them bells. As the charges get on that crispy rice, they are charged similarly. They have the same type of charge. And like charges repel each other. So as they both have negative charges, they fly away from each other to get away from each other. But again, I can block that because if I put it in a conductor, what electric field gets through the conductor? None. So even though I turn it on, nothing happens because when I have the conductor around it, we've shielded it from stray electric fields, and this is now safe from those electric fields, and the crispy rice does not get charged. We use a similar thing whenever we have cable TV. The coaxial cable that goes into your TV, it is shielded from stray fields. That way your TV doesn't ever get distorted. If you look at the signal wire, it's surrounded by the ground wire in order to keep any electric fields that might be around from getting to it. And that way you always get a good crisp picture from your cable. Okay? There's something else we can do with this. If I turn this on and turn out the other lights, I'm going to turn out some lights. You'll see this. You might see it spark a little bit there, okay, into me, so it's putting on charge. But I'm interested in the electric field around it. I have a little light here that if I hold perpendicular to it, you can see it light up a little bit. I hope you can see that in the camera. See it lighting up? But if I hold it this way, it's not. And that's because the electric field that comes out of here comes out at 90-degree angles. So when I have this at 90 degrees, it lights up. But when I have it not at 90 degrees, it doesn't. So holding it at 90 degrees, it's along the electric field lines and lighting up. Now, another important thing to note when you are drawing electric field lines is they always go from the positive charges to the negative charges. So if you look at some electric field diagrams, you'll see it go from the positive to the negative. It always goes that way. You can calculate the strength of the electric field as the force over the charge you put in it. So if you put a charge in an electric field, you divide that force by the amount of charge, and that's the strength of your electric field in newtons per coulomb. All right, that's it for my quick video. You guys have a good day.